In this video, we take a look at some applications of matrix operations in section 2.6. Our learning objective for this video is to use matrix multiplication to encode and decode messages. So we are working in the field of cryptography. So cryptography is when you encode a message or alternatively decode a message or a string of numbers or some other content. Cryptography is from the Greek word cryptos, which means hidden. And you may have seen cryptography in TV shows or movies about wars where people were using cryptograms to send encoded messages. You might also be aware that we use cryptography in computer programming. Anytime you do something like charge something to your credit card, your data is encrypted using code or a cryptogram, and most of those encodings involve matrix multiplication. They also involve keys and personal keys and things like that. So we're going to be studying the matrix multiplication and linear algebra aspects of cryptography in this section. So matrix multiplication can be used to encode and decode messages, and the encoded messages are called cryptograms. So to begin, you can assign a number to each letter of the alphabet. This is one way that we encrypt messages. And then the space you can assign a 0. So you can see A is 1 through Z being 26 here. And then we're going to use these numbers to convert the message into a row matrix. We'll do a 1 by 3 matrix. And then we'll include the spaces, but ignore any punctuation so we don't have to worry about periods or commas or anything. This is a really simple way of encrypting something. If you send data through a computer, you would use a more sophisticated way because something like this might possibly be able to be hacked, but we'll see how you could do it using linear algebra, and then you can think about, oh, what changes would you make to have a stronger encryption, and you can do some additional reading as well. All right, so down below we have the example of the message make it so, with spaces between make it so and then after so 2 spaces. And it was partitioned into 1 by 3 matrices. We're using 1 by 3 matrices because we're going to use a 3 by 3 matrix for our shift for the encoding. So you can see M corresponds with the 13th letter of the alphabet, A is the first letter, and K is the 11th letter. So those first 3 letters are the row matrix 13, 1, 11. And similar for the rest of the message. So E space I is the row matrix 509. T space S is the row matrix 20019. And the O with 2 spaces is the row matrix 1500. All right, so we're going to use this invertible matrix A, and we want to always use an invertible matrix because we need to be able to work backwards. So that's why we pick a square matrix. We're using a 3 by 3 matrix because our encodings were in row matrices that were 1 by 3. If we'd done 1 by 4 matrices to encode our data, then we'd use a 4 by 4 matrix. And so we're going to encode the message make it so. So we take each of our row matrices and multiply it by the encoding matrice. So when we take 13, 1, 11, which came from the letters M, A, K at the start of our message, and multiply it by matrix A here. So here's matrix A, here's MAK. This is our result over here. So this is the encoded part of the message. And then we do the same thing for the remaining letters. Here's E blank I, T blank S, S blank blank, and here are all our results in our sequence of encoded matrices. And then typically you remove the brackets and just have the string of numbers like in the last row here. So now if we want to decrypt the message, we got to work backwards. So we have to know the encryption matrix A, and this is where it comes in that A has to be invertible. So we're going to use A inverse to decode. So here's matrix A again. Here's a string that we're going to be decoding. So since we know A is a 3 by 3 matrix, we're going to assume this matrix is chunked out into 1 by 3 rows. So we'll partition it up like this. And then we start by finding A inverse here. And you could use SIMPy or any other computer program to do that. And then we take each chunk, each 1x3 row chunk, multiply it by A inverse and get our results here. So here are our string of results. And then we piece them all back together, and then we map each of these results to the corresponding letter in the alphabet. So B is the second letter, E is the fifth letter, A is the first letter. And so we get the familiar message. If you're a Star Trek fan, beam us up. All right, in the next section, we're going to look at some more examples of how we can apply matrix operations. We'll look at examples from finance and business applications, and then we're also going to take a look at how we find lines of best fit for data, common practice, and statistics.